Okay, Joanna, sync the clocks in 3, 2, 1, start. Whoa. Okay, here we go. So every minute I'm going to send her a message that it's been 1 minute. And every one of her minutes, she's going to send me a message that it's been a minute. It's been a minute. Still no message. Still no message from her that it's been a minute yet. Okay, I'm ready to send my second message. It's been 2 minutes.
It's been 1 minute. It's been 2 minutes.
Been 1 minute.
1 minute. That's interesting. I am already past 2.
It's been 1 minute.
Okay, she just barely said it's been a minute on her end. So at 3 minutes, I'm going to turn around and head back. It's been 3 minutes. Okay, we've switched directions now, heading back.
It's been 2 minutes.
Just got her 2 minute mark.
It's been 3 minutes.
Whoa, she's speeding up now. She's already at 3 minutes. Okay, almost my 4 minute mark.
4 minutes.
It's been 4 minutes.
It's been 4 minutes.
It's been 2 minutes.
Wow. He is slow.
This is getting weird. Okay, I'm coming up on the trip's end now. Around 6 minutes, I'm going to end my trip.
It's been 5 minutes.
It's been 5 minutes for her. Now she's ahead of my time.
It's been 6 minutes.
It's been 5 minutes. She's a minute ahead of me now. Okay, my trip's coming to an end. So as soon as it hits 6 minutes, I'll stop.
It's been 7 minutes.
I think that was a message. Okay, and stop.
8 minutes.
It's been 6 minutes. Okay, so I made it back. So at the end of the trip, okay, Joanna, how many minutes has it been on your end?
8 minutes.
Okay, for me, it's only been 6 minutes. This may seem like a paradox. How could you have two different people saying that the other person's clock is running slower? You have to first understand the theory of special relativity. Now, the theory of special relativity says that the closer you get to the speed of light, the slower your clock will appear to tick compared to an observer watching your clock. But the same holds true for you, the person moving. So while you're moving at near light speeds, people who are left on Earth, their clock will appear to run slower to you. And the rate at which the clock runs slower follows this equation here. So as I was moving away from Earth, it appeared like my wife's clock was running slower. And so because her clock was running slower relative to my reference frame on the spaceship, that means that I already should expect that when she says 1 minute is done, then it should be after when I say 1 minute is up, because her clock is slower. And according to the speed I was going, around 66% the speed of light, that should be at around 1 minute and 20 seconds that I should have expected for her to say a minute has gone by on her clock. But because I'm moving away from her, now I can expect that to be even longer because I'm moving away from the signal that she sent me. So she's on Earth, I'm moving away, and then she sends a signal at her minute, which is already delayed because her clock is delayed already. But then I'm moving away from it, so it takes even longer to get to me. And so I don't get that first minute signal until well after 2 minutes into it. And the same thing goes for her, because for her reference frame, my clock is the one running slower, and so I don't send it until after a minute has already gone by, well after a minute, around 1 minute and 20 seconds. And then it takes a while to get to her because my spaceship is moving away, and so it takes even longer to get to her. And so by the time she gets it, around 2 minutes and 20 seconds has gone by. So at that point, both of our time dilations are symmetrical. We both received the first signal well after 2 minutes. But then let's see when we both received the next signal. Well, for me in the spaceship, I didn't receive her next signal until after I had turned around on my way back, so well after the 3-minute mark. So now I'm on my way back, so even though her clock is still running slower relative to mine, I'm coming back into the signals. And as I come back into the signals, that means they're going to reach me more frequently, because she's been sending them off every minute, but now I'm coming back into the signals, so they're going to appear more frequent to me. So after 3 minutes, I get her minute mark about every 20 seconds. And so her clock is truly running slower relative to mine, but I'm coming into the signal, so it seems like it's going faster than a minute. And so her time seemed to have gone faster than my time. But in the end, by the time we ended up in compared times, I had lost out on 2 minutes of time. Now for Joanna, she didn't receive my first signal till around 2 minutes, and then she didn't receive my next signal till after 4 minutes because my clock is still running slow, and then she didn't receive my next signal till almost 7 minutes into it. And at that point, that's when my 3-minute mark was up, so to her, that's when I turned around and started coming back. And then from there, I'm heading on my way back, so I should be running into her signals frequently. So after that, it was around every 20 seconds or so. But I only got up to 6 minutes by the time I got back. And so by the time I got back, I had passed 6 minutes and she had passed 8 minutes of time. But the question is still, it's not very clear where I lost my 2 minutes of time. Why didn't she lose 2 minutes? Why was I the one that lost 2 minutes? And the best way to explain it is that the reason that I'm the one that lost those 2 minutes of time is because I'm the one who underwent an acceleration to turn around and come back. So on the way there, I was going at a constant speed, but then at 3 minutes, I had to stop, turn around, and come back. So I underwent an extreme acceleration. Now I didn't feel that acceleration very strong because it was undergoing an acceleration on every cell of my entire body, but still my whole body was feeling the force. And so because I was feeling that force, it was as though I was in a very strong gravitational field. And you may remember from general relativity that when you're in a strong gravitational force, your clock slows down relative to somebody who's not in that force. So basically, on my turnaround, I underwent extreme acceleration, which basically stopped my clock, and I lost out in around 2 minutes until I started going at a constant velocity again. So in order to resolve the twin paradox, or in this case, my return trip, the reason that I'm the one that lost the time is because I'm the one that turned around and came back. So whenever you change reference frames, you're the one that's going to experience a time dilation relative to somebody who didn't undergo those reference frame changes. Now remember that I said that the faster you go, the slower your time appears to tick relative to an observer watching you. So that means that as you approach the speed of light, your time basically stops relative to a person watching you. So that means for the light in our universe, for every light particle, every photon that exists, basically no time has gone by since the beginning of the universe. Now that's not just true for light. That also means that for a particle moving extremely fast, for example, sometimes we have protons that hit our atmosphere coming from the cosmic background radiation. They hit our atmosphere going at extremely high rates, around 0.999, 21 nines, 0.99999% the speed of light. So almost the speed of light, but not quite there. So for those particles, they've been traveling since the original Big Bang of the universe, and for us it's been around almost 14 billion years. But for those particles, it's only been around a month. So we figured out how to go forward in time. Now I have to figure out how to go reverse in time. But anyways, thanks for watching another episode of the Action Lab. I hope you enjoyed it, and thanks for watching, and I'll see you next time.